Today we'll discuss about nuclear energy. Myself, Chandrasekhar S. Patil from Sharad Institute of Technology, College of Engineering, Hyderabad. To begin with, we'll discuss about the brief history of nuclear energy. Nuclear energy was first discovered on 1934 by Enrico Fermi. The first nuclear bombs were built in 1945 as a result of the infamous Manhattan Project. The first plutonium bomb, code-named Trinity, was detonated on July 16, 1945 in New Mexico. On August 6, 1945, the first uranium bomb was detonated on Hiroshima. 3 days later, a plutonium bomb was dropped on Nagasaki. There is over 2 lakh deaths associated with these detonations. Electricity was not produced with nuclear energy until 1951. Mass and energy relation. Einstein suggested that mass and energy are related by the equation E equal to mc square. E is the energy, m is the mass, and the c is the speed of light, which is equal to 3 into 10 raised to 8 meters per second. Converting the mass of one penny could provide the entire energy requirements of 700 people for 1 year. Power a space heater for 7,000 years. That's about $3 million worth of electricity. Because mass and energy are related, the law of conservation of energy and the law of conservation of mass can be combined into the law of conservation of mass energy. Electricity generation from nuclear energy. Electricity can be generated from nuclear energy by two methods: nuclear fusion and nuclear fission. Nuclear fission reactions. The nuclei of heavy atoms are split under bombardment by neutrons. Means the heavy nucleus, heavy atoms are split by the bombardment of neutrons. Nuclear fuel cycle. In this, we will understand the nuclear fuel cycle with a brief explanation of how nuclear energy works, the enrichment process, and then power reactors. Initially, the mining takes place for the extraction of uranium. Uranium ore is usually located aerially. Core samples are then drilled and then analyzed by geologists. The uranium ore is extracted by means of drilling and blasting. Mines can be either in open pits or underground. Uranium concentrations are a small percentage of the rock that is mined, so tons of tailings of wastes are generated by the mining process. Milling and leaching. The ore is crushed into smaller bits, then it is sent through a ball mill where it is crushed into fine powder. The fine ore is mixed with water, thickened, and then put into leaching tanks where 90% of the uranium is leached out with sulfuric acid. Next, the uranium ore is separated from the depleted ore in a multi-stage washing system. The depleted ore is then neutralized with lime and then put into tailings repository. Meanwhile, the uranium solution is filtered and then goes through a solvent extraction process that includes kerosene and ammonia to purify the uranium solution. After purification, the uranium is put into precipitation tanks. The result is commonly called a yellow cake. Transportation. In the final processes, the yellow cake is heated to 800 degrees centigrade, which makes a dark green powder, which is 93% U3O8. The dark green powder is put into 200-liter drums and loaded into shipping containers and are shipped to fuel nuclear power plants. The mining leaders. We'll understand who are the mining leaders. Australia and Canada are currently the biggest uranium miners. The above mentioned process that takes place in Australia is exported because Australia does not have a nuclear energy program. The mining in Australia is primarily open pit. while the mining in Canada is mostly underground. There are two types of mining. One is open pit and second one is underground. Australia mainly has the open pit type of mining, and whereas the Canada has the underground type of mining. Conversion. To enrich uranium, it must be in the gas form of UF6, that is uranium hexafluoride. This is called conversion. The conversion is as done by Honeywell. First, the yellow cake is converted to uranium dioxide through a heating process. This step was also mentioned in the mining process. Then, anhydrous hydrofluoric acid is used to make UF4 is mixed with fluorine gas to make uranium hexafluoride. This liquid is stored in steel drums. Okay. Enrichment. Uranium enrichment increases the amount of U-235 in comparison to U-238. Domestic power plants use a mixture that is 3% to 5% U-235, while highly enriched uranium is generally used for weapons, some research facilities and naval reactors. Domestic reactors usually require uranium in the form of uranium dioxide, and the weapons use enriched mix in the form of a metal. The conversion and enrichment process is very dangerous because not the uranium hexafluoride is radioactive, it is also chemically toxic. In addition, if the uranium hexafluoride comes in contact with moisture, it will release another toxic chemical called hydrofluoric acid. Next, we will understand about fuel fabrication. After being enriched, the UF6 is taken to a fuel fabrication facility that presses the powder into small pellets. The pellets are put into long tubes. These tubes are called fuel rods. A fuel assembly is a cluster of these sealed rods. Fuel assemblies go in the core of the nuclear reactor. It takes approximately 25 tons of fuel to power 1000 megawatt reactor per year. Picture on the right is the fuel assembly. Transportation. Radioactive materials are transported from the milling location to the conversion location, then from the conversion location to the enrichment location, then from the enrichment location to the fuel fabrication facility, and finally to the power plant. These materials are transported in special containers by specialized transport companies. People involved in the transport process are trained to respond to emergencies. Nuclear fission. When a sufficient amount of fissionable material is brought together, chain reactions occur as shown in the diagram. So the reactor types are PRW, pressurized water reactor, BRW, boiling water reactor, RBMK, graphite moderated pressure tube boiling water reactor, CANDU, Canadian deuterium uranium type of reactor, Magnox, gas cooled reactor, AGR, advanced gas cooled reactor, fast breeder, high temperature gas reactor. Nuclear fusion reactions. There are two opposing forces in the nucleus. Electrostatic forces. Positive proton repels the positive proton. Strong force, that is nucleons attract each other. The strong force is stronger but acts over a shorter distance. Adding more nucleons is favored with small nuclei. Nuclear fusion reaction is a combining together. Atoms are fused together rather than split apart. Possibilities for nuclear fusion are much greater than nuclear fission reactions. Here, deuterium and tritium are combined to form helium and neutron is released along with energy. Nuclear fusion reactions. In order for fusion reactions to occur, the particles must be hot enough, that is temperature is considered, in sufficient number, that is density is considered, and well contained, that is confinement zone or confinement time. These simultaneous conditions are represented by the fourth state of matter known as plasma state. In plasma state, electrons are stripped from their nuclei. A plasma therefore consists of charged particles, ions and electrons. It means that in the plasma state, the electrons are away or removed from the nucleus, from the atom, and only nuclei is there are charged particles, that is ions and electrons and charged particles are there in the plasma state. Temperature up to several million degrees centigrade are reached. There is no substance on this earth that can tolerate this high temperature. So how is plasma confined then? Tokamak technology, magnetic confinement. Efforts to control fusion first relied on the principle of magnetic confinement, in which a powerful magnetic field traps a hot deuterium tritium long enough for fusion to begin. So it is magnetically confined to the confinement time, or to the fusion to begin. That duration, it is confined in the magnetic confinement field. In November 1997, researchers exploiting the magnetic confinement approach created a fusion reaction that produced 65% as much energy as was fed into it to initiate the reaction. This was achieved in England at Tokamak facility, a donut shaped vessel in which the plasma is magnetically confined. So this is the pictorial view of Tokamak fusion reactor. This is shown here. Advantages of nuclear energy. It is clean form of energy and does not generate any carbon dioxide. So there is no any byproduct like carbon dioxide. Nuclear power plants do not require a large working space. Means the area of the nuclear reactor is not as much compared to other types of energy sources. It is highly concentrated form of energy. Means it is highly compact and concentrated form of energy. It is very cheap compared to other forms of energy. Negative impacts of use of nuclear technology. Nuclear bombs. There is a negative impact that nuclear bombs can be generated. Reactor mishandling. If there is any reactor mishandling, the fuel or the nuclear fuel can get leaked and it may harm the ecosystem. Waste dumping in case of fission reaction or fission energy. There is a huge requirement or there is a huge work in the waste dumping in the case of fusion energy, and it is also a bit risky. Life of nuclear reactors is only 40 to 50 years. So here this is what all about we have understood about the nuclear fusion and the nuclear fission reactions and the nuclear reactors, and how the plasma in the nuclear fusion reaction is confined in the magnetic confinement zone, that is Tokamak reactor. So this is all about nuclear energy. Thank you.